Thanks for sticking around. I probably wouldn't have. But yeah, so recently my colleague Angus and myself, we've been working on designing and implementing a new fraud detection system at GoCardless. I found out that this chap from Stripe was doing a similar talk on their fraud detection system, so I decided to talk more about the unbalanced data aspect and a little bit less about the fraud detection, but that's also included as like a secondary thing. So, I'm going to start with some of the boring stuff, sorry. What is an unbalanced data set? So, a data set is unbalanced when the class of interest, or the minority class, is much rarer than the other class or classes, and they're called the majority classes. And what happens is the classification rules that predict the small classes, they tend to be fewer, they tend to be weaker than those that predict the prevalent classes. And what you end up is with test samples belonging to the small class, which are misclassified more often than those belonging to the prevalent classes. Why is this bad? So often the cost of missing a minority class is much higher than that of missing a majority class. So as an example, take cancer diagnosis. If you misclassify someone who doesn't have cancer as having cancer, then the worst that can happen is that they'll go on to have further tests. If you misclassify someone that does have cancer as not having cancer, you know, it's pretty shitty, really. So the performance of machine learning algorithms is typically evaluated using predictive accuracy. That's the default in a lot of the scikit-learn classifier modules. But if you've got a base rate of 99% for the majority class and you're trying to optimize based on accuracy, really the most intelligent thing to do there is to label everything as the majority class. When we were doing the fraud work, we were using the cross-validation module in scikit-learn, and actually there's a really nice scoring input parameter on the cross-val score function, and you can actually alter that so that the default is accuracy, but you can change that to recall, precision, F-measure, G-mean, etc., etc. So that's definitely something to remember. So I'm going to launch right into some more interesting examples. So, this is a satellite radar image of the sea surface, and these images are typically used to detect oil spills. These oil spills, they originate from ships mainly, and the oil slicks are actually less reflective of radar than the average ocean surface, and so what you end up with are these black regions on the images. So the one on the right is the oil slick. You also get a load of lookalikes, and these derive from natural phenomena like algae, rain, wind shadows. And unfortunately, or fortunately, however you want to look at it, the lookalikes occur way more frequently than the oil slicks. And so you end up with a hell of a lot of false positives when you're working, or you can end up with a hell of a lot of false positives when you're working with these data sets. That's a really cool paper, by the way. Okay, another example. We've already touched on this, the diagnosis of cancer. I actually found it quite difficult to find a good image for this slide, but an example that I did find was using histopathological data to generate features for machine learning. And this particular paper actually goes into, it approximates the mapping between the data in the original feature space and the transformed data in the PCA embedding space. But one of their big problems is with the fact that the original data set is massively unbalanced. Sorry. Okay, and my third example is fraud detection, and this is the one that is kind of most pertinent to us. There are a few papers out there on machine learning in telecommunications fraud, and employee fraud, in payment fraud, and this is kind of like sparked quite a lot of interest because it makes a lot of sense financially to kind of pull out all of these fraudulent cases and stop them at source or as soon as possible, because it costs money, and boy does it cost us money. Sorry, I don't know. Okay, so GoCardless. What is GoCardless? We're an online direct debit provider. We serve around 800,000 people in the UK and abroad, and I'm sure everyone here uses direct debit. You probably aren't aware of the mechanism that's kind of behind this payment type. And so what happens is a merchant will establish a relationship with a customer, and they want to exchange money, or the customer wants to pay the merchant. Direct debit is a really cheap payment option for the merchants. Our fees are a hell of a lot lower than kind of fast payments. And so what happens is the customer will go cardless, or transfer money into the go cardless account. We pay it out to the merchant. And the whole process from start to finish takes between 4 and 5 days. And so actually it's a fairly shoddy way to make money if you're a fraudster, because we've got a hell of a lot of time to catch you. And so we're a startup, we're fairly young, we're 4 years old, and up until recently we've been using a fairly basic clunky system. And the kind of the ratio of fraudster to non-fraudster in our data set is around 2%. And so formerly we used a discrete set of rules that we chose using Bayesian logic. Over time we've added more and more rules. It's kind of created a system which is actually really, really quite messy. And we've had to employ a team of fraud analysts that go through all of the data manually. And we have fraud alerts which are created automatically, and a lot of which are redundant, but it's kind of, we're trying to cover all bases. So this is how we're doing, and actually we're not doing too bad at detecting the fraudsters. Our aim is to have a recall of 1, and we almost do have a recall of 1. If you like, the current method that we've got in place is like an ensemble method, but without the machine learning. So there are different stages at which we can catch a fraudster, but we always eventually catch them at some point or another. So yeah, at the moment we've got a recall of around 100%. The precision is 8%, and we thought we could do better. So we decided to build a classifier, and we used the obvious Python libraries. We also used Seaborn, and this is the first time that I'd used Seaborn. It's pretty cool for data visualization, especially when we're presenting to the rest of the company. So something maybe worth checking out. So to start off, as always, a quick and dirty model. And on the left-hand side, you can kind of see a basic outline of the pipeline that we use for this dirty model. We tried a few different classifiers. We've got a framework in place that makes it easy to test out all these different classifiers. And the random forest classifier actually performed the best. We were able to get a precision of 8%, so that didn't change, but the recall was significantly less than 1. And over here I've actually normalised the merchant base to 1,000 to help you get a better sense of the numbers. So where do we go from here? Clean your data. I cannot stress this enough. Angus and myself, we sat down for 3 days going through all of the data, and what turned out was merchants that were classified as fraudsters weren't actually fraudsters. They were bad use cases a lot of the time. What's a bad use case? For example, chaps that sell boiler insurance to old people. They've legitimately or been granted access to that person's account. The person has set up the direct debit. It's not such a noble way to make money because they don't need that service. So we don't want to serve those people, but really they're not fraudsters, so they shouldn't be included in our model. And we sat down for 3 days, Angus and myself, and he likened it to the job that the YouTube reviewers have to do when they look through graphic content, because actually it was soul destroying. Okay, so once we cleaned the data, we decided to resample it. So this is a data level approach to addressing the class imbalance, and there's a few ways that you can resample the data set. Undersampling is an obvious one. It's very easy. You effectively remove random instances of the majority class until your two classes are sufficiently balanced. And the problem with undersampling, we found, is that it gave great model statistics, but we lost a hell of a lot of information, and we ended up with a model that didn't generalize very well. And so we eventually went down the route of oversampling. It's kind of a bit more difficult to show oversampling on a graph, so I've made the data points thicker to show you that we've kind of overlaid some on top of each other. And so obviously with oversampling, you duplicate, triplicate, replicate the minority class until you get the same class balance that you're looking for. And then briefly, I want to go through another technique that we came across. We actually haven't gone down this route, but it's worth explaining. It's fairly new, and it's called synthetic minority oversampling. And it effectively involves creating synthetic examples of the minority class. So I'm going to quickly go through the technique. Okay, so this is the original data set, and I'm just going to remove the majority class to make it easier to see. So let's assume here that the amount of oversampling that we want is 200%. So we choose a sample, and for each sample we want to select the k nearest neighbours to it. You should decide upon k. I've decided upon 5 in this instance. Okay, and we want to oversample by 200%. So we randomly choose 2 neighbours from the k nearest neighbours. And then at this point we want to generate 1 sample in the direction of each of the 2 randomly selected nearest neighbours. And you want to generate that sample along the vector, joining the original sample with one of the other points. And what I've got here is the oversampling graph that we actually used, that we went with, and the synthetic minority oversampling technique graph on the right-hand side. And you can see that SMOTE actually forces the decision region of the minority class to become a lot more general. And it's been shown to yield successful results in a few studies that I've read. So, back to fraud. It's all well and good saying that we need to oversample or resample the data set, but how do we go about doing this? Scikit-learn is a babe because in Scikit-learn 0.14 we kind of struggled with altering the class weights, but in Scikit-learn 0.16 a lot of the classifiers now have a class weight as an input parameter on the classifier itself. I think all excluding Gaussian or naive Bayes, to ignore that. And this saves you a hell of a lot of hassle of having to manually upsample and desample. And so we added a few more steps to our pipeline. Obviously this pipeline should be a closed loop, it's an iterative procedure. But we added grid search and feature selection, and in the end we came up with a logistic regression model. The recall was very close to 1. Our precision we were able to increase to 40%, so that's a 5-fold increase, and it's something that our fraud team is really excited about. This is an overly simplistic explanation of the system that we've implemented. Like I said before, there are different stages at which we can catch a fraudster: prepayment, prepayout, blah, blah, blah. And there are different models that we have to implement for each stage. Okay, so we've covered a few data level approaches to addressing the class imbalance, and it's worth mentioning some algorithm level approaches. So cost-sensitive learning is one of them, and the goal here is actually to minimize the cost of misclassification. And to do this, implementation is actually very similar to the resampling approach, and you still use the class weight parameter, but you choose the class weights manually based on the cost matrix which you've come up with the business team. And I want to go through another technique. So this is, I guess it's an algorithm level approach, but it's called ADA boost or adaptive boosting. We actually didn't use this on the fraud stuff. We've been using it on some other work that we've been doing, but we've generated some good results with it. So again, thought it was worth going through it. ADA boost is short for adaptive boosting, and it's effectively a meta estimator that you can use with a whole range of classifiers. It's adaptive in the sense that you fit a classifier. Once that's been fitted, you fit subsequent weak learners, and they're tweaked in favour of those instances which were misclassified by the previous classifiers. That sounds like a bit of a mouthful, so I'm going to quickly go through the procedure. So you begin by fitting a classifier on the original data set. So that's the decision boundary. And you can see that there were 3 data points which were misclassified. And so we want to re-weight those incorrect misclassifications more heavily for the next classifier that we fit. So there we fit the second classifier. And you can actually repeat this process any number of times, depending on how much time you have. And there we have a third weak classifier. And the final classifier is actually a weighted combination of all the weak classifiers. The alphas are chosen to minimise the overall training error, and there are lots of variants on adaptive boosting. You should look in ensemble methods in scikit-learn. And finally, while I was doing kind of my research for this talk, I came across a couple of other interesting techniques which people are using to clean their data. And so atomic link removal, the goal here is to remove borderline examples. So atomic links are points that are each other's closest neighbours, but which don't share the same class label. So you can see them encircled in green on the left-hand side. And what you do there is you remove them, and it kind of makes the border between the 2 different classes a lot more distinct. And then there's condensed nearest neighbour. The goal here is to remove instances from the majority class that are very distant from the decision border. And effectively what you're doing is you're selecting the subset of samples from the training data such that the one nearest neighbour with the subset can classify the examples almost as well as one nearest neighbour with the whole data set. Okay. And so, just to finish, I just want to briefly talk about what our project on fraud detection means for the company, because that's kind of where all of this work into addressing the problem with imbalanced data sets came from. So we're introducing the new fraud system at the moment. It's a gradual process. Obviously, we don't want to introduce any breaking changes. But based on the feature importances that we've derived from the work that we've done so far, we've already switched off certain fraud alerts, so that's already reduced the burden on our team of fraud analysts. We were really happy that the best model was the logistic regression, because it's something that is very easy to explain to the rest of the company. And what we intend to do is to provide a fraud score to the fraud analysts on the scale of 0 to 1, so that they can read from the dashboard what features are contributing to such a high fraud score when it occurs. And finally, there are certainly other considerations or other things that we need to consider which we haven't. Stationarity, this is a common assumption in many time series techniques, but we know that the mean, the variance and the autocorrelation structure of fraudster behaviour is likely to change over time. It's something that we're monitoring. And finally, I think it was Ian that mentioned earlier today about keeping your model as simple as possible. Lots of people have suggested to me using neural networks and other nonlinear algorithms. But for us, the main challenge has been, cleaning the data, engineering more features. That takes a hell of a lot of time. And through just doing that and oversampling, we've been able to get a model which is significantly better than the one that we're currently using. So I finished a bit early, but if you have any questions, happy to answer them. Do you want to go ahead?
How do you define fraud?
How do we define fraud?
Yeah, your approach in your company,
Yeah.
from financial perspective,
Yeah.
and also the human can not be a fraud, but do something wrong. wrong because you forget something or something like that?
Okay, so direct debit is slightly different. A merchant will sign up to our company, so sign up to our service, and what they will do is they will have acquired a load of customer details, stolen customer details, maliciously, and what they do is they create direct debits on behalf of those customers, and direct debit is essentially a pull mechanism, so they pull the money out of those customers' accounts, and then the customer will get in touch with us because on their bank statement they see Go Cardless. They charge back to us. We're chasing money from the merchant. So it's a little bit different to Stripe in that money switches hands via Go Cardless. And I don't know if you went to the fraud talk yesterday, but
basically it's claims of your customers that they were fraudulent.
Exactly. But I mean, we try to say if a fraudster has an email address which was previously used by a fraudster, we flag that as fraud before they defraud the customer. Obviously, we want to detect them as early as possible, not after they defraud the customer, because we do have a 5-day lag between the payment being initiated and being actually carried out. So it's kind of beneficial to all parties if we act as soon as we can. Hi.
Hi, thanks for the talk. I really wish I was going to But one of the things I was interested in
Yeah.
is that when you're using the data,
Yeah. Yeah, I don't know, sorry.
but when you were talking about is it what made it
That's a good question. We actually have been using Ada Boost on a different project, not on the fraud project itself, and we're getting good results with that model, but we actually haven't. We're kind of at the early stage of that project, so we haven't been looking a lot into the feature importances. One thing that was interesting actually was when, just on the subject of feature importance, when we initially ran our models without balancing the data sets, Random Forest came out as the best model, and when we looked at the feature importances that were generated, it just didn't make sense intuitively, you know. And so, you know, the accuracy was obviously very high because the base rate is so high. But it was only once we'd done the resampling that you kind of, you know, the results actually match your intuition, and that's like huge because, you know, machine learning is working off the experiences of humans, right? We're not, and that's something that we've actually had to explain to people in the company because there'll be a new type of fraudulent behaviour, and they come up and they go, test this, and we say, not fraud. They say, you're wrong. And we say, well, next time it will catch it, you know, we'll just retrain the model. Yeah.
You say you have to do resampling with the pathway.
Yeah. Yeah, that was helping. Yeah. Sorry.
Thanks for the talk. Just curious. The model, when you evaluate the model, what's the kind of positive, what's positive
Okay.
numbers you think would be feasible?
Okay, so the question is, when we evaluated the model, what false positive rate and false negative rate we would be?
False positive number and true.
For the false positive rate and the true positive rate. Okay. Well, so I was thinking in terms of recall and precision, but with us, with Go Cardless, a lot of the risk is on us if we don't catch the fraudster. So we aim for a recall of as close to 1. So we want the true positive rate to be 100%. You know, as far as the false positive rate is concerned, it's very much a trade-off between the costs of hiring, you know, many fraud analysts and the cost of having a huge chargeback that we have to deal with. So we aim for, you know, our model kind of performance be based on true positive rate, and that, you know, any improvement that we can get in precision or the kind of false positive rate is a bonus to us. You know, it's. Hi.
If you label them as actors, you will rely on manually take the case by case.
So if we detect them as fraud, so at the moment we've got a precision of 40%. If we detect them as fraud, we have the fraud analysts actually go through them and all of the other ones. Not only the true positives, but also the what turn out to be false positives, and they manually mark them. But at the moment, I mean, fraud is just there's a lot of clever people out there trying to defraud us, and it's taken up a lot of time. So that was what spurred on this project, and that's what motivated it. And yeah, it's already generating some good results. So, hi. Oh, what transform? So it's he's a fraudster because he's interested. What transformations we've done on the feature space? To be honest, I don't want to go into too much detail on the features that we're using. It's like a fairly sensitive topic. Things like emails, we used data that we acquire from the merchants when they sign up. We also looked at their payment activity and dynamic features as well as static features. So their kind of activity using Go cardless within the previous 5 days, say. There are some... Angus, can you remember any other weird ones? Or not the features themselves. Oh, what did we do? Yeah, we did, means of structure normalization, but on the features itself, we didn't, in terms of engineering them, I can't think of a good example offhand. I think it was choosing the features that was a bigger part of the process as opposed to engineering them, as opposed to altering them once we'd got them. Hi.
Have you considered using some provided methods for novelty detection? Detection?
Yeah. So like a one-class classification. Yeah, exactly. That's another algorithm level approach to addressing the data imbalance problem. Yeah, we considered it, and kind of went down the easy route first, probably, and yeah, something that we might consider looking at in the future. But right now, we don't need to. We've been using anomaly detection on something else recently at Go Cardless, which is looking at fraud more on a payment level than on a merchant level. Yeah. Is that it? Thank you. Thanks.